Greetings everybody, and in this video we're going to be taking a look at the definition of a ring as well as some examples. So as for the definition of a ring, this definition can change depending on which source you look at. So what I'm going to do is I'm going to provide a bit of a general definition. However, there's a specific definition of a ring that we're going to be using throughout the entire course. A ring is a triple. We have R and then these two, well, symbols over here. So what is R over here? R is just a set, and well, these two guys over here, these are binary operations. So maybe you recognize them as plus and multiplication. No, that's exactly what we call them. These are binary operations. Well, what does that mean precisely? It means that it takes two elements of your sets and gives you back another element of your set. Well, maybe for this plus map over here, it's a map that takes two elements of your set and gives you back another element of the set, and we might write it as AB, and well, this gets mapped to the plus of A comma B over here, where this plus we kind of understand as a function on, well, this R cross R here, this Cartesian product. But just for convenience, we don't really write it like this, so we put the operation in between the two elements that we're, well, adding together in this sense. And the same goes for multiplication, so they're just binary operations at the moment. So a set with these operations, well, that wouldn't be too interesting, so it must satisfy some conditions. So I'll write it out as follows over here. I learned this trick from Friedrich Scholar, if you've watched his videos on YouTube before. So these are the axioms for the addition operation, and then you also have some for the multiplication as well. Now, technically, I'm not supposed to write out all of them. I'll show you which ones to drop in a minute. And then finally, we got a distributive law as well, which involves both plus and multiplication. So Kani, it helps you memorize the following. So the first one is commutative for the addition. So this tells you that for all A and B in your set R, A plus B is just B plus A, so it doesn't matter the order in which you add the two, addition is commutative. Next up we have A, that stands for associative, which means for all A, B, and C in your set R, we have A plus B. If you add these two guys together and then you have A plus C, well, you could add B and C first and then add A at the front. So associative means it doesn't matter which pair of parentheses you add together first. Next up, the N stands for neutral. So this is your additive identity, which says that there exists some elements called 0 in your ring, such that for all elements A in your ring, we have the following: 0 plus A equals 0. So sometimes we call this 0 the additive identity. Next up, I stands for inverse, which says that for all elements A in your ring R, there exists some elements that we call minus A in your ring R, such that if you take your element A, you add it with the inverse, you get back to the additive identity. So in this sense, the N axiom over here has to come first before you have this inverse. So for every element in your set, you should be able to find another element in the set where if you add the two together, you get back the 0. In fact, as a side note, if you've studied group theory before, you'll notice that this makes R with addition an abelian group. Okay, so those are the axioms for addition. How about for multiplication? So this is where things might change up a little bit. So we'll start off with A actually. This is associative. So in all definitions of a ring, this is the one that kind of survives. So similarly to addition, for all A, B, and C in your ring R, if you multiply two elements together and then multiply by another element on the right, well, you could multiply these two guys first and then multiply A on the left. And then I'll get to the distributive law next, actually. So the distributive law just links addition and multiplication together. So it says for all elements A, B, C in your ring R, if you have A times B plus C, this equals to AB and then plus AC. So you can distribute this element A into the parentheses as you usually would. And the same goes for the other direction as well. If you have A plus B and then times C, this is equal to AC plus BC. Note that we need these two at the moment because we haven't assumed that multiplication is commutative, which means AB might not necessarily be equal to B times A over here. So in the most general definition of a ring, this is what we have. There are only 6 axioms over here. Now, in some sources, the definition of a ring might include C and N as well. So it might impose the condition that the ring is commutative as well as having a multiplicative identity, so this neutral element. And in fact, the definition that we're going to take for this series is going to involve these 4 axioms for the addition, as well as it being a commutative ring with identity. And all rings are associative anyways. In fact, you don't really want this I over here because once you include the I, then your ring is actually something called a field, which is something we'll study later on. But as for the other two axioms, if multiplication is commutative, then you actually call it a commutative ring. So for all A, B in your set R, if you have A, B, that's just B times A. And note, if we have two elements, we can just stick them together, and that assumes that there's a multiplication in between them. And as for the neutral, this just says there exists something called A1 inside of your ring R, such that for all elements A in your ring, you have that 1 times A is equal to 1. So that's called the multiplicative identity. And in fact, because we're working with commutative rings over here, we don't really need this second distributive law. You only need that second distributive law if your ring is non-commutative. So a remark, for us, a ring is commutative with identity. And if you say this, well, this kind of refers to the multiplication, obviously, because addition is always commutative in a ring, and it always has an identity in a ring as well. But do realize that in different sources, rings might drop the commutative axiom as well as this neutral axiom as well. But we just include them so we can make our rings nicer, so we don't have to care about left multiplication and right multiplication and so on. So let's take a look at some examples of rings to finish off the video. So if you take a look at the set of matrices, which are n by n in size, over let's say the complex numbers, doesn't really matter, this is not a ring. Well, this is for us at least, because depending on the definition that you choose, matrices do form a ring, but for us, it doesn't form a ring, unfortunately. Specifically because this commutative axiom is violated. What's another example? Well, a Z is a ring with integers because addition forms a group and multiplication satisfies these axioms as well. It's commutative, associative, and the neutral element is in there because 1 is inside of Z. Q is also a ring. The rational numbers, the real numbers also form a ring. The complex numbers are also a ring as well. In fact, these three over here are also fields. In fact, fields are a special type of ring. We also include this multiplicative inverse axiom here. So that gives us another example for free. All fields are rings. However, if you take a look at the set of natural numbers, which is n, this is not a ring. Why is it not a ring? Well, you just take a look at the addition axioms. In particular, this inverse axiom is violated because the negative numbers aren't in there. So axiom 4 is violated. Now, something we'll take a look at in the next few videos is how to create new rings, in particular how to adjoin elements to rings. You can take a look at something of the form, let's say Z adjoin I. So this is something that you call the Gaussian integers. It's the set of all numbers of the form A plus BI, where A and B are in the integers. So this guy is a ring as well. You can check the axioms, and this is true. None of the axioms are violated. However, if you take a look at the sets, let's say R is equal to A plus B times the cube root of 2, where A and B are integers. Well, it looks similar to the Gaussian integers I wrote up above here, where I interchanged the I with a cube root of 2. However, unfortunately, this guy is not a ring. Because to be a ring, if you take two elements of your ring, you multiply them together, you still need to be inside of the ring. And you can see that's not satisfied because if you take cube root of 2 times the cube root of 2, well, this is equal to the cube root of 4. These two elements are inside of your ring R, but this guy that you get out on the other side is not in the ring R. So in particular, this guy is not closed under multiplication. So you can't write the cube root of 4 as some A plus B times this cube root of 2. Another good example is, well, the integers modulo n. So let's take Z mod 4z, so the integers modulo 4. This guy's definitely a ring. You can check the axioms. So something I want to point out about this ring over here, let's take an element, let's say 2 for example, and let's multiply it by another element, let's say 2. Now notice that 2 and 2, they're not equal to 0, but if you multiply them together, you get 4. But inside of the ring Z mod 4Z, this is really the same thing as, well, 0. So inside of a ring, you might get the situation where you have two non-zero elements, A and B, multiplied to give you 0. So A, B not equal to 0. And this doesn't happen in a field, for instance, where if you have the product of the two elements equal to 0, then one of the two must be equal to 0. And the final example is the set of functions from the real numbers to the real numbers. So this is the set of all functions f which take you from R to R. There's no condition on the function being continuous or anything, just any function will do. This is also a ring because addition is commutative, associative, there's neutral elements which is, well, just the 0 function, and there's also the inverse as well, just take the negative of that function. And if you take a look at the multiplication axioms, well, associative clearly holds. It's commutative as well. There's the neutral elements, which is just the one function, and there's no need for the multiplicative inverse. So functions from R to R is a ring, but it's not a field because not all functions will have an inverse, because sometimes you might divide by 0 and, well, that's not good. So that's basically everything for this video, just the definition of rings as well as some examples. So next time we'll take a look at a few nice things you can prove with the rings, and we'll also introduce polynomial rings as well, and in particular make this construction of adjoining elements to an existing ring already more precise. So I hope you guys enjoyed the video, and I'll see everyone in the next one.